In the last module, I discussed the fitting, reporting and interpretation of an MLRM model. In this session, we are going to see another illustrative example where we are going to again fit, interpret and report an MLRM model. Let us now see as to how to fit an multiple linear regression model for a savings function. So, here this is the model that we are going to fit. Y hat is equal to beta naught plus beta 1 x 1 plus beta 2 x 2, where y hat is the dependent variable, and in this case it is annual savings given in 1000 rupees. The first independent variable in our example is x 1, that is annual income, which is again in 1000 rupees. The second independent variable x 2 denotes family size. So, let us see as to how to fit the savings function MLRM model. So, we got to estimate as usual the estimators beta naught hat, beta 1 hat, beta 2 hat, followed by R square value for goodness of it, adjusted R square, that is R bar square, variance of all these three estimators, standard errors of beta naught hat, beta 1 hat, beta 2 hat, and finally the F statistics, which helps us to identify whether the model is significant. So, here is an example of fitting an MLR model for the following data, and this data is concerned with the savings function. So, Y is annual savings, x 1 is annual income and x 2 is the family size. So, for computation purpose we can change all these rows into columns. So, the first column is Y, second x 1 and third is x 2. So, how to go on with other computed values? So, how to compute the other values? So, we compute small y deviation from y in fourth column, x 1 small x 1 deviation from x 1 in fifth column, deviation from x 2 in the sixth, and we have small y square in the seventh column, small x 1 square eighth, ninth column x 2 square, small x 2 square, followed by multiplied value of small x 1 and y, small y in 10th column. 11th column represents small x 2 multiplied with small y values, and the 12th column represents small x 1 multiplied with small x 2. So, how to go on? First we have to find the small y deviated value of y. So, the answer is y minus y bar. So, how to go on with y bar? Y bar is nothing but sigma y by n. So, the total up value of y, all capital Y values, is 36, 36 by n. Here the number of data set is 7. So, the answer is 5.14. Here I am approximating the value to 2 decimal points. So, substitute here to get the deviated y value. So, y minus 5.14. Let us look at the first case. 5 minus 5.14 gives us minus 0.14. So, in all the values in the fourth column is proceeded as we did in the first case, and we get the other values in this column. The same way we go to the small x 1 value generation. So, how to do it? Capital X 1 minus x 1 bar. So, the average or mean value of x 1 is calculated as sigma x 1 by n, this is equal to 45 by 7. So, the summation of all x 1 values is 45. So, 45 by 7 is 6.43, again I have approximated it. So, we use this value to derive small x 1 values in the fifth column. So, let me look at the first case. 6 minus 6.43 gives minus 0.43. Proceed likewise for all the other generation of values of small x 1. The sixth column, as we did for small x 1, we do for small x 2. Here it is capital X 2 minus x 2 bar. So, how to derive this average or mean value of x 2 bar? It is again sigma x 2 divided by n, and sigma x 2 here, the total up value of all x 2 values is 28. So, 28 by 7 gives us 4. So, substitute 4, and the first case, if you look at the first case, it is 4 minus 4 0. and go with the second and third, and you get all the values, small x2 values in the sixth column. So, now the seventh column is small y square, which is nothing but the squared values of all the y's given in the fourth column. So, the first value if you see minus 0.14 into minus 0.14 gives us 0.0196. So, follow the procedure and find the other values. Total up all the values, small y square values, and get sigma small y square, which has to be taken up for other estimations. The eighth column is small x1 square. So, just as we did for y square, the fifth column values has to be squared up. So, the first case is minus 0.43, minus 0.43 into minus 0.43 gives us first case value of small x1 square, that is 0.1849. So, proceed likewise for all the other values and again total it up. So, when it sum it, you get some sigma x1 small x1 square equal to 27.7143. So, this is our total small x1 square value. The ninth column is x2 small x2 square, which is nothing but the squared value of all the elements, all the values in sixth column. So, first case 0 into 0 is 0, next minus 1 into minus 1 is 1, and we go on squaring up the other values. So, total it up. So, sigma small x2 square, the total is 18 and keep it there. The next column, the 10th column is the multiplied value of small x1 and small y. So, here where is small x1? Look at here, it is in fifth column. So, fifth column multiplied with small y is in fourth column. So, multiply the values given here, corresponding values. So, first case if you see it is minus 0.43 into minus 0.14 and the answer that we get is 0.0602. So, proceed likewise for all the corresponding values of x1 small x1 is y in 4 and 5 column and multiply it to get the values in 10th column. Sum it up. So, summation of small x1 y gives us 30.5714. The 11th column, just as we did the previously, this is small x2 into small y. So, where is small x2? It is in sixth column. So, sixth column multiplied with the values given in fourth column. So, we have 0 into minus 0.14 in the first case. So, the first case is 0. If you look at the next case, it is minus 0.43 into minus 1.14, which gives us 1.14. So, proceed likewise to obtain the other values and total up all the values that we have generated. So, the answer is summation of small x2 y equal to 24. The last column, the 12th column, is the multiplied value of small x1 and x2. Repeat. Now, let us see how to compute the 11th column, which is multiply value of small x2 and y small y. So, go to column 6 where you have small x2 values and multiply the values, corresponding values given in column 4. So, the first case is 0 into minus 0.14, which gives us 0, and the next case minus 1 into minus 1.14, which gives us 1.14. Proceed accordingly for finding the other values. So, sum it up to get summation of small x2 y, which in this case is 24. The final column is 12th column, where we multiply the small x1 values with the corresponding small x2 values. So, in this case we have those values in 5th and 6th column. So, the first case is minus 0.43 into 0, which gives us the first value 0. Similarly, minus 0.43 into minus 1 gives us the second value 0.43. So, proceed the step as we did and find the other values in this column. So, last we just sum up all the values given. So, we get sigma x1 small x1 x2 is equal to 21. So, the summation of small x1 small x2 in this case is the value 21. Now, let us see how to compute beta 1 hat. We already know this formula as we did in previous illustrative example. It is sigma small x1 y into sigma small x2 square minus sigma small x2 y into, that is multiplied with sigma small x1 x small x2, and this is whole divided by sigma small x1 square sigma small x2 square minus sigma small x1 x2 the whole square. Just substitute the values that we have already obtained in the table. I am taking only the approximated value, that is to 2 decimal points. So, sigma x1 y in this case is 30.57, sigma small x2 square is 18 minus sigma small x2 y we obtained is 24 and sigma small x1 small x2 value that we obtained is 21. So, we substitute it, and below it we have the denominator sigma small x1 square 27.71, sigma small x2 square 18 and minus sigma small x1 x2 is 21. So, in this formula we have square value. So, we have to put power 2. So, multiply these terms, you get an answer, while 24 and 21 again an answer. Denominator also we calculate and find it as 57.78. The numerator here in this case is 46.26. On dividing these two numbers, we get the answer 0.8. This is again approximated. So, if you look at beta 1 hat, in this case the value we obtain is 0.8. Similarly, proceed with calculation of beta 2 hat, and the formula as we already know is given here. So, sigma small x2 y in this case is 24, sigma small x1 square value for 27.71 minus sigma small x1 y 30.57, sigma small x1 small x2 21. Substitute all the values. Since the denominator as in previous case is the same thing, I am just using the same value here. So, 57.78. This multiplied value is 665.054 and here the multiplied value is 641.97. On subtracting, you get 23.07 by 57.78 and the answer we derive is 0.399, as usual approximated. So, beta 2 hat in our case is 0.399. The third element is beta naught hat, estimator beta naught hat. So, it is a very simple formula, y bar minus beta 1 hat x 1 bar minus beta 2 hat x 2 bar. Substitute y bar 5.14, beta 1 hat that we have already computed 0.8, x 1 bar is 6.43, beta 2 hat is 0.399 and x 2 bar again is 4. So, on substitution and computation and calculation, what we get is minus 1.6. So, beta naught hat here the value is negative minus 1.6. A very important element next is r square, the stating the goodness of it. Formula is beta 1 hat sigma x 1 y plus beta 2 hat sigma x 2 y by sigma y square. So, as we have already calculated in the tabular forms, we use all those elements here. Beta 1 hat calculated 0.8, sigma small x 1 y small y 30.57, beta 2 hat that we have calculated 0.399 and substituted, then sigma small x 2 y the value was 24 that we obtained. So, we substitute here. Sigma small y square that we got is 34.86. Again let me tell you, we have approximated it to 2 decimal points. So, on computation and adding up all the terms, you get 34.032 by 34.86, answer 0.976. So, in this case r square is 0.976, again approximated. The fifth one, variance of error term, which is denoted as sigma hat square, is given by the formula sigma e square by n minus k. and first we got to find sigma e square, and the formula for sigma e square is 1 minus r square sigma small y square. We have already found r square. So, let me tell you, we cannot find sigma e square or sigma hat square without r square. So, substitute approximated value 0.98 and sigma small y square is 34.86. So, on subtracting 0.02 multiplied with 34.86 gives the answer 0.6972. Sigma e square is 0.6972. The variance of error term sigma hat square, when we substitute sigma e square and n 7 k 3, 7 minus 3 is the denominator, when we divide we get the answer 0.1743. So, sigma hat square in our case is 0.1743. Now, variance of beta 1 hat. So, sigma hat square already calculated, has to be substituted. Sigma small x 2 square 18, sigma small x 1 square, and all these elements sigma x small x 2 square minus sigma x 1 x 2 whole square as already computed 57.78. When we divide the terms we get the answer 0.0543. So, in our case variance of beta 1 hat is 0.0543. Now, let us get to the 7th step of finding variance of beta 2 hat. Sigma hat square, as we already know, 0.1743, sigma small x 1 square 27.71 approximated value again, and the whole denominator as in previous case it is 57.78 substituted, and then on dividing, multiplying and dividing, you get the answer 0.0836. So, variance of beta 2 hat is 0.0836. Let us now find variance of beta naught hat. As we already did in the previous illustrative example, the formula is given here. So, we just substitute the values that we have obtained. Sigma hat square 0.1743, n in this case is 7, which is the number of data set, x 1 bar 6.43, and according to the formula square it up. Sigma small x 2 square 18 plus x 2 bar is 4, so square. Then sigma small x 1 square is 27.71 minus 2 into x 1 bar 6.43, x 2 bar is 4, sigma small x 1 x 2 small x 2 is 21. Substitute all the values, calculate and compute it, and you get the numerator as 107.3282. The denominator as usual is 57.78. You just substitute it here. 1 by 7 is 0.143. So, when we compute the whole thing given in this bracket, we get the answer 2.0005. Multiply the terms, the values given, and you get 0.349. So, variance of beta naught hat in our case is 0.349, which is again an approximated value. The 9th step is finding the standard errors of all the estimators, which is nothing but finding the root of variances obtained. So, for beta naught hat, root of variance of beta naught hat gives us 0.59. Standard error of beta 1 hat is root of variance of beta 1 hat, which gives us the value 0.23. Standard error of beta 2 hat is the root of variance of beta 2 hat, which gives us the value 0.29. R bar square, also called adjusted R square, is calculated using this formula. So, here in this formula R square as we obtained is 0.98, substitute it here, n is 7, n again 7, and k, the number of variables is 3. So, the next step 1 minus 0.98 becomes 0.02, and 7 minus 1 is 6, 7 minus 3 is 4. So, on multiplying this term you get 0.03. 1 minus 0.03 gives the answer 0.97, which is the value for R bar square. The next final step is calculation of F star statistics, and the formula is given here. N is 7, k is 3, R square is 0.98, k is again 3, and R square 0.98. Substitute the values. 7 minus 3 gives you 4, 3 minus 1 gives you 2, and on multiplication and on division you get the answer 98. So, F star statistics in our case is 98. Look at the template for reporting. Followed by this template, we are going to report the savings function that we have obtained. So, here the savings function is y hat is equal to minus 1.6 plus 0.8 x 1 plus 0.399 x 2. So, what is this minus 1.6 is beta naught hat, 0.8 beta 1 hat, 0.399 beta 2 hat. The next row denotes the standard errors that we have obtained. So, for beta naught hat it is 0.59, beta 1 hat 0.23 and for beta 2 hat it is 0.29. The t statistics value can be computed by dividing the value of the coefficient and the standard error obtained. So, for beta 1 hat the t statistics is 0.8 by 0.23 giving you the answer 3.48. Similarly, we can calculate t statistics for beta 2 hat. So, 0.399 by 0.29 gives us 1.38. On the right side, we denote the f star statistics calculated, which is 98, r square value is 0.976 and r bar square which is 0.97. So, go to the statistical f table and t table to find the table value at 5% level of significance. So, for the first case f at 2,4 degrees of freedom, the table value is 6.94, while t table value at 4 degrees of freedom is 2.776. We have to use these table values for the next interpretation. Now, let us interpret the result. The result shows that the model is significantly different from null model, since the calculated f value, that is 98, was found to be greater than the table f value 6.94. The r square value 0.976 shows that 97.6% variations in y is explained by x 1 and x 2. The r bar square value 0.97 confirms that the model is a best fit. The result further shows that x 1 significantly influenced y, that is, annual income influences annual savings of the family. This is because the calculated t statistics of beta 1 hat, which is 3.48, is greater than the table t value 2.776. But the coefficient of family size x 2 is insignificant. This is because the calculated t statistics of beta 2 hat 1.38 is less than the table t value 2.776. Now, since beta 2 hat is insignificant, we will not interpret the value of the regression coefficient beta 2. In general, the regression coefficient which are insignificant are not interpreted. In this case, beta 1 hat is significant, so we are interpreting the value. For an increase of 1000 rupees in annual income, on an average the annual savings of the family increases by 800 rupees. In this module, you learnt how to fit, report and interpret a multiple linear regression model, that is a savings function model. So, in the next module we will see some more examples. Thank you.